Hey everyone, welcome back to The Explainer. Today we're building the ultimate biological catalyst revision guide. If you're tackling A-level or FSC biology, you are in the right place because this is an absolute goldmine. We're going to unpack all the high-yield facts about enzymes, their structures, and the really fascinating thermodynamics that make them tick. I want you to think about this for a second. Why would cellular processes like, say, DNA replication, or even just digesting your breakfast, be completely impossible without biological catalysts? Well, it's a fundamental problem of biology. Without enzymes, life's chemical reactions would just happen way, way too slowly to keep us alive. We're talking about processes that would normally take years, getting done in literally milliseconds. These tiny molecular machines are the only reason we actually function on a livable timescale. So here's our game plan for today. First, a quick biological catalyst overview. Then, we'll look at enzyme chemical composition, followed by the apoenzyme versus holoenzyme showdown. After that, we'll cover lowering activation energy, dive into transition state theory, and finally, wrap it all up with a 10-second summary. All right, let's dive straight into Section 1, Biological Catalysts Overview, or, as I like to call them, life's little accelerators. So, by definition, an enzyme is a biological catalyst that speeds up a biochemical reaction without getting consumed in the process. Simple enough, right? But wait, there is a massive exception here that examiners love to test. While nearly all enzymes are globular proteins, some RNA molecules, which we call ribozymes, also have catalytic activity. You definitely want to keep that little exception in your back pocket. Let's quickly rattle off the core features of these biological machines. First up, their catalytic nature. They accelerate reactions without undergoing any permanent changes themselves. Second is specificity. Every single enzyme has a completely unique active site. It's kind of like a super specific lock and key. Third, they are incredibly sensitive to their environment, especially when it comes to temperature and pH changes. Fourth, a lot of these reactions are totally reversible. And lastly, regulation. The cell can actually tightly control enzyme activity using specific inhibitors or activators. Moving right along to Section 2, Enzyme Chemical Composition. Let's look at the actual anatomy of a catalyst. Now here is a high-yield equation you absolutely need to memorize. Apoenzyme plus cofactor equals holoenzyme. I always find it helps to think about it like a car. The apoenzyme is essentially the car's frame and the engine, right? It's the structural framework. But sitting on its own, it's totally inactive. It's not going anywhere. The cofactor, on the other hand, is the key. You put the key in the ignition and boom, you get a fully functional, active vehicle, which in biology we call the holoenzyme. And this brilliantly illustrates exactly how that works. You can see how the structurally sound but completely incomplete apoenzyme framework perfectly accepts that cofactor puzzle piece to form the holoenzyme. Without that non-protein addition, the enzyme really is just a parked car. So that key we just talked about, the cofactor, can actually come in 3 different types. First, we've got coenzymes. These are organic molecules, they're loosely bound, and they usually come from vitamins. A really classic example here is NAD+. Second, we have prosthetic groups. Now, these are also coenzymes or metal ions, but they are tightly, permanently bound to the enzyme. Think of the heme group in cytochromes. And third, metal ions. These are inorganic cofactors like magnesium or zinc ions, and they are absolutely essential for activating and stabilizing the whole setup. Okay, on to Section 3, apoenzyme versus holoenzyme. This is our core comparison. So the crucial point here is seeing this stark contrast between these two states. The apoenzyme is protein only. It's structurally unstable and honestly completely inactive. It needs a buddy. The holoenzyme, though, is the full package, the combined protein and non-protein cofactor. It is stable and highly catalytically efficient. To put that into perspective, an inactive apolilactate dehydrogenase has to bind to its coenzyme, NAD+, to finally become the fully active holoenzyme, lactate dehydrogenase. Next up, Section 4, Lowering Activation Energy, or the physics of the push. Before we get into the physics, we need to define activation energy, which you'll usually see written as E sub A. In the Arrhenius model, this is the absolute minimum amount of energy that reactants must have for a chemical reaction to even happen. Think of it like a giant thermodynamic hill. Even if a reaction is destined to happen, those reactant molecules simply must push over this vital energy barrier to transform into products. Without a little push, they're just going to stay exactly as they are. Now, what's really interesting here is how dramatically the enzyme changes this landscape. See that massive peak? That represents the activation energy for an uncatalyzed reaction. It's a huge hill to climb. But by bringing in a catalyst, that curve drops significantly. The enzyme drastically lowers that required energy peak. It's kind of like it just tunnels straight through the hill, making it incredibly easy and fast for reactants to turn into products. Let's see how this builds into Section 5, transition state theory, and that unstable peak. So how exactly does an enzyme pull this off? Let's step through the milestones. First, the substrate binds to the enzyme's active site. Second, stabilizing non-covalent forces, we're talking hydrogen bonding and van der Waals forces, start locking things into place. Third, and this is the absolute secret sauce, these favorable interactions release free energy, which is known as binding energy. And finally, step 4. That newly released binding energy basically forces the substrate into a highly unstable transition state. The active site is essentially hugging the substrate into an optimal fit, breaking old bonds and prepping new ones. All right, listen up because this is a massive exam trap. An enzyme does not change the equilibrium points of a reaction. I'll say it again. It does not change the final thermodynamic destination, and it doesn't change the amount of product you ultimately get. All it does is speed up the rate at which you reach equilibrium by lowering that activation energy barrier. It is such a common trick for examiners to suggest enzymes alter the overall free energy of the reaction. Seriously, do not fall for it.
We're in the home stretch. Section 6, the 10-second summary and final review.
Okay, let's lock this in. Here is your rapid-fire 10-second exam summary. Number 1, enzymes function by lowering activation energy. Number 2, the active holoenzyme is always the inactive apoenzyme plus a cofactor. Number 3, the binding energy released at the active site is what drives the substrate into the transition state. And number 4, our favorite exam trap, enzymes absolutely do not change the overall reaction equilibrium. To wrap up this explainer, I want to leave you with a bit of a provocative thought. We've just seen how utterly perfect these molecular machines are. But if a simple protein structure holds the thermodynamic key to all life, what do you think happens to a living system when just one specific cofactor, say a single vitamin or a tiny little zinc ion, goes missing? The fragile precision of biology really is mind-blowing. Thank you so much for exploring this with me. Keep reviewing these concepts and good luck with your exam prep.